Hello, everyone. My name is Ethan, and my presentation today is about a research project conducted under the guidance of Professor Gando Min of the College of Engineering Technology and his graduate student Hamad Alvi. It is titled Design and Development of a Soft Variable Stiffness Robotic Finger. Let's get started. A brief overview of this presentation and what I'll be going over today. First, I'll go over an introduction to the field of soft robotics, then dive into the engineering objectives of this project, then the design of the finger, 3D modeling, and finally the future work that we have planned for this project. So if you've never heard of the field of soft robotics before, it is a rapidly emerging field that utilizes soft and elastic, often 3D printed materials to create actuation and just perform robotic movements in general. If you've seen the movie Big Hero 6, you'll know that one of the main protagonists of the story, Baymax, is a great example of a soft robot. He really shows how these soft robots can interact with objects such as tennis balls and other devices, as well as just interacting with humans in general because of their safe, user-friendly nature. So some of the engineering objectives we had for this project was to design a soft finger similar to the one seen on the right, and implement a variable stiffness mechanism into this finger. And I'll go over what the variable stiffness really means in a second. We wanted to 3D print this finger fully, and we wanted to potentially apply this to fields such as the rehab field, just like the medical field in general, as well as deep sea or deep space exploration. So the design of the finger is based off this design on the right. And this is our predetermined design, and this is where we'll be implementing the variable stiffness mechanism. The variable stiffness mechanism just means that we'll be able to selectively choose where some areas are stiff in this soft finger, and therefore make it rigid and not able to bend. This is important because the soft finger works off this bending motion. Once it is filled with air through this chamber, the air goes through this winding pattern and inflates these channels. And as the channels inflate, they cause this finger to bend downwards towards the left of your screen. And if we're able to selectively choose where we want the finger to be rigid, we can change the behavior of the bending and thus change how it bends. And we wanted to use pneumatic power for actuation for controlling whatever this variable stiffness mechanism was, to go in line with the pneumatic power that powers the entire finger. And thus we go into 3D modeling for the design of this variable stiffness mechanism. And you can see that two designs were outlined on the right of your screen. One that was what we like to call externally controlled, and one that is internally controlled. So the first design, the externally controlled, uses pneumatic cylinders to push pins into these three slots. And let's say this slot on my laser pointer has a pin in it. And once this pin is engaged, as the finger begins bending, this entire area from the slot to this chamber is unable to bend because of the pin, while the rest can bend downwards. And this will thus have this variable stiffness mechanism and be able to successfully change the behavior of how this finger bends. So now we go into the pros and cons of this design. So one pro is that this design actually employs magnets at the end of this actuator in this slot to align with the support beam and thus be able to push this pin into the slot. But unfortunately, because of this magnet design, it requires an additional support beam, as you can see in this picture, to go along with the finger. And this will ultimately increase costs in printing time and material needed. Secondly, this is our design that utilizes an internal control, as we like to call it, of these pneumatic cylinders that extend or retract blocks in this soft finger. And you can see that each of these slots have these this blue block and a lighter blue pneumatic piston to push and pull. And some pros and cons of this design is that firstly, it is contained within the actuator, which is a great benefit, as well as needing less material for the whole design because of the unneeded support beam as seen in design 1. Unfortunately, this design does have less room for error because there is no magnetic or other type of alignment, and thus, if this finger was bent too much, and like I have one that's 3D printed here, you can see that it bends quite a bit without any force on it. If it is out of alignment, there is a potential that these blocks cannot go into the finger and thus cause some error. So finally, we have some future work for this project, which is the first step is to print and assemble the designs for the soft robotic finger. And then we can test and analyze each of these designs for their effectiveness by measuring specific parameters to determine actuation speed of the finger or power draw, such as the PSI needed to control the finger, and electric power draw, and more. And finally, our third step is to reiterate and redesign this concept for improvements based on the tests that we used. And we can apply this finger into areas such as the medical field and more once we have successfully redesigned and feel satisfied with our project. These are some of the references that we consulted for potential solutions, as well as just what was going on in the field of soft robotics, to find any to find anything that we can do to improve this field. Finally, I'd like to acknowledge Dr. Gandol Min and his graduate student Hamad Alvi for their support once again for this project. And finally, thank you for listening to this talk. And if you have any questions, please email my Purdue email, ethan.a.zane.1@purdue.edu. Thank you again.